Okay, thank you. So I'm going to give you a brief overview of several projects that the collaboration that I'm working with are doing about nearby galaxy observations with this NIKA2 camera, which is an array at the IRAM 30-meter telescope that observes at 1.2 and 2 millimeters of wavelength. So I'm first going to give you a brief motivation of why what we do is important. Then I will tell you about a specific project dedicated to dwarf galaxies, because those galaxies are specific objects with a low metal content that impacts the properties of the dust. Then I will review a few projects that we do also on normal galaxies, trying to really give a description about the ISM properties and the spectral shape of the SCD in these objects. And then I will finish by doesn't work. Okay, so first, introduction. So to put everything in context, so let's look at the spectral range, I mean, the SCD of a typical galaxy. So you see, I put all the spectral, I mean, if you like wavelength, frequency, energy, I didn't put Rydberg on wave numbers, but you will probably have a scale that you like. So first, of course, we have the stellar populations. A part of this radiation is absorbed by the ISM. So we are interested by the thermal emission by dust, here, this curve here, the way it changes as a function of environment, and deriving the physical properties of the grains at the origin of this emission. There is also the gas emission. So we are not so much interested into the lines. I mean, there are more contamination for us because we are really working on the continuum. But we are interested in the free continuum here, and also in the synchrotron continuum at long wavelength. So there is also something I will briefly mention, which is the anomalous microwave emission, this emission bump here, AME, that originates from the spinning grains. So it's a centimeter emission that I will briefly mention. And I will also talk a lot about here, this component here, which is called the sub-millimeter excess, which is simply a deviation from standard dust models that we see in some objects. And I will talk to you about. And as you see, the NIKA2 camera observes in this spectral range. So that's really what we are probing. So, so why is the millimeter regime interesting? So the millimeter continuum emission, I'm not talking about lines. Because so the millimeter spectral energy distribution, it's an important dust mass tracer, because in the millimeter emission, it's where the emission is dominated by the cold content. And so it's really crucial if you want to give an accurate dust mass estimate of your cloud or of your galaxies. And also, I mean, the dust mass is often used as a proxy to infer the total gas mass of a galaxy, for example, at high redshift. And there are a lot of uncertainties about the long wavelength optical properties of dust grains. So it can be looked at the opacity of the grain. Because first, I mean, the observations are complicated, and also even in the laboratory, there is a lot of variability. But the dust mass estimates that we do all rely on the assumption of these optical properties. And so that's why we really need to have a good empirical understanding about how these optical properties change as a function of the environment. And talking about environment, we are focusing about nearby galaxies because they give us a wide diversity of physical conditions that we can probe. So you have dwarf galaxies, like this example here, that are small but cute, that have relatively a low metallicity, so a low abundance of heavy element, but a high gas fraction and a specific star formation rate that is often relatively high too. Then you have normal galaxies that have average everything. And you have elliptical galaxies that are also interesting because they have a rather high metallicity, a rather low gas fraction, and also a specific star formation rate that is quite low because they have depleted most of their gas. So I was talking to you about this sub-millimeter excess, so I'm going to tell you a bit more about that. So it is, as I told you, an emission excess that we observe in some specific regions, so especially in dwarf galaxy or low metallicity environment. What I'm showing you here, it's an SED of one region in the Large Magellanic Cloud that has a relatively high dust column density. So you see, in this case, we are trying to look at the deviation around the 500 micron point. So at high column density, no excess. And then when you go to low column density, you see that you have a larger systematic deviation. So it's something that cannot be accounted for by any molecular lines, not by the free continuum, not by the residual from the CMB fluctuations. It's really something that when you look at its distribution, follows more or less the structure of the galaxy, but it's more prominent at low metallicity and at low surface brightness. And if you look at a global scale, here it's another blue compact dwarf galaxy. You see that with the standard dust model, you have also an excess emission that cannot be accounted by free, and that takes us here. So this excess has been studied a lot in the literature. Myself, I look at it once every 10 years. So it's something that it's not really an artifact. It's something that has really been observed and confirmed by different people with different instruments in different objects. So I give a list of a few authors here in dwarf galaxies. It has also been seen in the Milky Way. It has been observed. And the trend that I showed you before, the fact that the strength of this excess decreases with the dust surface density is also confirmed in the Milky Way at 500 microns. So there has been several scenarios proposed in the literature to try to explain what could be the origin of this excess. So there was the fact that it could come from very cold dust. So that was a very simple explanation, but it would need to account for a very large fraction of the total mass that would be concentrated in a few small dense clumps. And the fact that it doesn't work when you look at the spatial distribution with excess, which tends to be very diffuse and anti-correlated with the density. So there are other explanations. So that's the fact that it could come from some solid state effect, some temperature-dependent optical properties. That's an effect that is also seen in the laboratory. There are some optical properties that show really a change of slope in the submillimeter regime. But the fact that it depends on the temperature makes it difficult. Makes it very difficult to explain the observational trends, which doesn't seem to depend very much on the temperature, but rather on the column density. And then there was also a model proposed based on the magnetic properties of some inclusions into the grains. That is interesting because there are polarization tests that can be done to try to see if this effect is real or not. But again, it's difficult to explain the variability that we see because it would mean that we would destroy these particles as a function of the density. And finally, the spinning dust for the AME that I showed you before was also invoked, but it needs to be combined with other processes. So it's not really a likely carrier. So the point where we are now is that we have a few observations where we have good spatial resolution, but only at short wavelengths. So we have a rather weak constraint. And a few large-scale observations, for example, with Planck, but where we lack the spatial resolution. So that's why we actually need to have a good spatial resolution at millimeter wavelength, which is why NIKA2 is very important for this type of project. And the issue with NIKA2, and with a lot of the millimeter observatories, that it really offers a unique opportunity to really make sensitive map of large regions of galaxies that are, above 10 arc-minutes in size. But the signal is quite weak. And there is an important contribution from the atmosphere that needs to be removed. And so it means that we are suffering from a problem of filtered flux, which means that we need to, when we reuse the data, use the information from other observatories such as Planck or ICT to recover the diffuse emission that we are missing. And from a modeling point of view, also, this is quite complex because there are some contribution from the galactic sources and from the cosmic infrared background that we need to take into account. And there are numerous physical conditions that contribute to that, as I showed you before. So, now talking a bit about a program that we have at the moment with NIKA2 about dwarf galaxies. So we have observed a few galaxies. So you see at 1.2 and 2 millimeter, that's a blue compact dwarf galaxy. We have another one too that has a lower star formation activity. And we have a third one that will be observed next week. And we are modeling the spatially resolved spectral energy distribution of these galaxies to try to see how the semi-millimeter excess varies with the physical condition. So we have homogenized all the data. We use the Themis model within the hierarchical Bayesian code Herbie. And we look at the way, for example, the residual at 2 millimeter, which is really the strength of the excess. It's a relative residual in percent as a function, for example, of the starlight intensity. We see that there is no clear trend. And it's consistent with what was found before, that it's not, this excess really doesn't really depend on the temperature. But if we look at the way it varies with the surface density, we see that there is some trend, even some scatter, and we are still fine-tuning this model, but it's confirmed. And so this case, it's the first time that we really have the spatial resolution in a rather low metallicity environment to really look at the way this excess varies. So what we are doing right now, we are trying to interpret this trend with a simple model. So we are working, we have a work in progress, a working hypothesis, where we are trying to look at the fact that the strength of this excess varies inversely with the column density might be the fact that is linked to the mantle growth on the grain. And if you look at the grain opacity, for example, of some silicates, amorphous carbon, and that now you make a composite of both growing carbon mantle on top of silicates, you are going to see an effect like that. So it's appearing, yes. So you see you can flatten a bit the slope. And so it means you can smooth out the excess that you see. So that's, there are a lot of combination of grains that we can try and that we are slowly starting to do. And the idea is to do that, to explain the variation of the excess. So a few minutes, yeah. So I'm now going to tell you a bit about a study of normal galaxies. We are part also of a guaranteed time program with the NIKA2 instrument that is called Imaging, that is really targeted at rather large galaxies. So here I show you a few images at 2 millimeters of some of the sources that we have. In total, we have 22 galaxies. And the idea is that now we are going to have a lot of statistical information to really show how the opacity of the grain varies as a function of the conditions. What is the contamination, I mean, the contribution of the different components of the radio continuum. So as I told you, we need to feather those data using Planck and ICT data. And so I'm showing you a few projects. So for example, we have a PhD student in our collaboration who worked on 2 irregular galaxies, doing some spectral decomposition in the far higher to radio wavelength to constrain the contribution of the SED, and also to study the way the beta, so the slope, I mean the emissivity index of the dust grains varies across these galaxies. We also have another PhD student who looked at this edge-on galaxy, NGC 891. So you see at 1.2 and 2 millimeters. So that's really the disk. It's 89 degrees inclination. And so model again with the same approach with my model. What we did is that we did a spectral decomposition at different wavelengths as a function of radius and elevation. So you see here I'm showing you what happens in the disk and the halo. And this axis corresponds to the radius across the disk. So that's the center and the different size, different wavelengths, and showing the contribution of you see the three, the dust, synchrotron, and free. And so you and so you see that basically, so there are not so much difference as a function of radius, except in the center where you see the bulge of the galaxy, but it's quite homogeneous. But you see a quite large difference between the disk and the halo, especially concerning the synchrotron contribution, because I mean the magnetic field in these galaxies really follows the outflow. And so it means that we will do that for all the galaxies in our sample. And so we'll have a way to really build SED model that can be parameterized by the type of galaxy and the physical condition, the gas fraction, the star formation rate, that can be applied to more distant galaxies. And also, we are interested in general dust evolution in galaxies. So here I'm showing you just a plot from one of my postdocs. So that's a galaxy that's M99, still observed with NIKA2. And we have looked at the way the fraction of small amorphous carbon varies as a function of the radiation field. So this axis, this QIF, it's the mass fraction of the small carbon grains that are responsible for the emission of the aromatic features. So the mid-infrared bands. And that's the intensity of the radiation field. So that's equivalent to an equilibrium temperature of the grains. And the fact that we have a trend that's with some scatter, but that decreases, it's a trend that is quite well known, that tells us that when you have a higher, I mean, more intense radiation field, you tend to destroy those small grains. But again, that's one of the first cases where we can really observe this trend at this spatial resolution in these galaxies, because most of the trends present in the past were actually among galaxies, integrated. Yeah, so that's what I say. So just as a takeaway, so I hope I try to convey that the millimeter range is really important because it has really been poorly observed in the continuum for nearby galaxies in the past. And that's understanding the way the millimeter grain opacity vary is really crucial to be able to have a reliable dust mass estimates. About the sub-millimeter access, so I showed you that we have a program trying to study it and confirming really its presence and its variation. So this excess is really more prominent at low metallicity, and it correlates negatively with the dust column density. And we are trying to explore the fact that the variability of the excess could be due to the removal of mantles on the grains in very diffuse regions or at low metallicity where the conditions are also very harsh. And about gas-rich galaxies, so we have 22 gas-rich galaxies that have been observed and that we are analyzing. And we are currently using this data to better constrain the Fahrenheit opacity, decompose the spatial continuum, and study dust evolution. And just before concluding, I'm making a quick add that we are opening 4 postdoc positions, so in France, 2 in Saclay, 1 in Grenoble, and 1 in Toulouse. The deadline is November 8th, so if you are interested or if you know someone who could be interested, talk to me. And we're also organizing a summer school, so François talked about it this morning. So it's the last 2 weeks of July. A lot of famous speakers, a lot of hands-on. The registration will open sometime in January, February. So again, if you're interested, come talk to me. Thank you.